Chemotherapy is a painful, expensive, and not always effective way to treat cancer. What if we say that a more efficient way that allows to reduce dosage, control its toxicity, and target tumor cells only, already exists? Nanoparticles. The usage of nanoparticles as drug carriers can change the whole cancer treatment strategy, making it possible to cure people efficiently and increase recovery rates. For evaluating nanoparticle designs, different efficiency metrics can be used. A common one is SOSA, Solvent Accessible Surface Area, which is important for drug delivery. After a nanoparticle is created, it takes some time for it to reach a stable state, and the SOSA amount drops by that time. Producing and testing different designs in a lab is very expensive and time-consuming. That's where molecular dynamics comes to help. The goal of molecular dynamics is to monitor the change of efficiency metric in a computer-based simulation. It is an affordable solution, but still takes weeks to go through the simulation.
Our team is introducing an efficient way of applying machine learning to predict the stable state of nanoparticle design and its efficiency value. In that way, the approach would massively reduce the simulation time and complexity and help nanoparticle scientists deliver new cancer cures faster.
But how do we feed such a big nanoparticle structure into the predictive model? Descriptors come to rescue. Descriptors encode a nanoparticle into a simpler structure. They make sure each design of the nanoparticle has the same representation regardless of its rotation or permutation. The chosen descriptor is called Many-Body Tensor Representation, or shortly MBTR. MBTR descriptor can extract the global properties of the nanoparticle using different element pairs and their interatomic distances.
We propose an approach based on two machine learning models. The first one, we have developed a time series model that could predict the movements of the nanoparticles based on its previous positions for as many time steps in the future as required. Also, based on the structure of the nanoparticle, it is possible to predict the efficiency metrics. So the second machine learning model maps the predicted MBTR values to its corresponding SOSA value.
The nanocarrier is administered. It travels to the target tissue, where the difference of polarities with the solvent and molecules on the surface cause constant vibration of the surface molecules. As a result, the solubility of the drug residues keeps changing.
One key challenge of the task was to model the interactions among the drug and background molecules with the solvent. So we decided to use the attention-based transformer model for MBTR forecasting.
Transformer model is based on a multi-head self-attention mechanism, in which each token of an input sequence is compared to other tokens to gather and learn dynamic information over time. In this way, the model can identify and learn important interactions within columns inherently.
As the data for training is also derived from molecular dynamic simulations, we had a very limited amount of data to get proper accuracy with a large model such as the transformer. But as the MBTR vectors represent different physical systems, through probabilistic models we could synthesize a lot more data. With this, the overall system works with a very acceptable amount of error.
The problem with deep learning model is only the conclusion is seen, not the output between levels. As a result, we have no idea how the nodes are analyzing the data, and that is the AI black box problem. Now that we have a model that can predict the efficiency, it is important to understand how it is happening, what features the model picks the most, what are the correlations between the initial nanoparticle and the efficiency of its stabilized version. That's where the explainable AI comes in. Explainable AI is an AI tool that produces results for human to understand and explain a certain predictive model. Explainable AI will be able to give some transparency to solve the black box problem.
And this is what we intend to do with our EVO-NANO project. We will implement a model composed with explainable AI to help us to get valuable insights without any doubts on the decisions that the model is taking.
We will also create an interface as a bridge between the experts and our implemented models. They will be able to upload the first few time steps of the nanoparticle design, and our models will determine if the nanoparticle design showed efficient metrics or not.
Then, the experts will be able to choose the best nanoparticle designs of their choice and do the time-consuming simulations. In the end, our tool will be able to save the precious time of the experts by not testing the faulty designs. And that's all for our video. I hope you enjoy it, and goodbye.